All right, now let's talk about what's special about triangle similarity. As a reminder, to show that two shapes are similar, we needed three things before. We needed that they were the same number of sides. We needed all the same angle measures. And then some sort of consistent scale or internal factor. Now, this last one you may have found was important when you were looking at rectangles. So, for example, all rectangles have four 90-degree angles. And so we may be tempted to say, okay, all rectangles must be similar, but they're missing that third scale factor. You may notice that if I try to take this shape and pull at the corner, which keeps the consistent scale factor, this will never look exactly the same unless I adjust the internal ratios to match. So we need some sort of consistent scale or internal ratio or scale factor. However, triangles are a bit of an exception. And let's talk about why. So, you may remember that we had some special congruence criterion for triangles. So the congruence criterion for triangles were side, side, side. They were side, angle, side. Angle, angle, side, and some people consider angle, side, angle as different from angle, angle, side. I personally don't, because in either case you end up knowing all three angles. But either way, these are congruence criterion. Now, think about our visual definition of similarity, where there's some distance you can hold the two objects away from a viewer where they line up perfectly. In other words, there's some distance where they appear congruent. What does that mean? That means with each congruence criterion, there must be a similarity criterion. So for side, 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 there is similarly a side, side, side criterion for triangles. Notice in that case, we don't need angle measures. So if I number my three parts of our similarity definition, this one only uses parts 1 and 3. It only uses a consistent scale or internal factor between all the sides and the same number of sides. We don't need angle measures because triangles are special since they only have three sides. There is similarly a side, angle, side similarity criterion. This is where they have one angle the same and the sides it's between are proportional between triangles. So let me give an example of that. So let's have this thing create a nice little triangle for me. And let me create a similar triangle here. Now, this smaller triangle, let's say that we know between these two triangles, both of them have a 30-degree angle. And I don't know exactly how long these are. I'm just going to kind of eyeball it. Let's say this one is 7 inches and this one is 8 inches. If this one is 3.5 inches and this one is 4 inches, so we have a consistent scale factor only with those two sides. That's enough information. The third side will be forced to have the same side length. So let's say we knew this side was 4 inches. It's probably not that. There's actually some cool math you can do to figure out what that side length would be exactly. In fact, I'm going to figure out what that side length is going to be exactly real quick. So, okay, y'all, you won't believe this, but I went through and did the math, and it actually is about 4.001 inches. So I was actually within a thousandth of an inch. I'm kind of proud of that. Anyway, so to find this last side length, we would just need to divide by 2. That's guaranteed. We don't need any more information. This allows us to implicitly measure sides. So this one uses all 3 criterion, but not completely. Instead of all angle measures, I only need 1 angle measure. And instead of having a consistent scale factor between all 3 sides, I only need to use 2 sides.